classes, but you don't have to.
Yeah, and
I
I think
think,
I really want to do
that-
to make one combination. And then
Okay.
there is probability theory worker, and then there is advanced probability.
Okay,
test and
great.
it would be like concentration for
Okay. So you're taking
Good
it
idea.
as audit. Okay.
Yeah.
Hey, how are you?
So actually, we just see the. To see the big announcement about the. This time.
Yeah. It's the hardware is all installed, the software is.
You mean the queuing system or the.
No, I mean, like, only one version of PyTorch works right now.
Okay, I mean the.
And you have to build, no, the latest version,
The latest version.
but nightly, nothing else.
Okay,
And you have to build almost anything you want from scratch.
okay. But you have the ability to do that, or you will also take it with it.
You have the ability to build it yourself,
Okay,
but you don't get, you can't use Docker,
okay.
so. It's
That's a. So you have PIP install everything by yourself?
you can't even do control.
Okay, now we're going to.
Compile, build from scratch. So some things are installed now, but a lot of stuff is not. So it's just a little crazy right now.
I see. So a lot like from Para or like most of this actually it's the some version works.
Yeah, no, those are way much more mature,
Oh, okay.
but we're getting there.
I see.
Yeah.
So. Like for example, you want to do the old skills.
Well, you have to build it. Yeah, there's nothing installed right now. So like a lot of packages that you would want to download from like signal base or something, they require a different version of Python. Even that'll crash.
I see. So the best of all like
We can't get Alpha to work on it.
Okay. So the big one you have to follow like the real version.
It's a universal problem with this GH200s. Because they're on processors, not x86.
Oh, okay. Now I only think that.
But we're getting
Baby, the
we're getting close. Like, if you have an important project, you know, you need some examples like sending email. But if you're on. Anyway, I mean, Sanjay and I are gonna send out a call.
Okay. I can have a. Yeah. So like we do the typical like a pipeline, so as you and stuff.
Yeah, but you know, but if you have like a really important project, you need to get it now.
Yeah, we kind of like able to get it so from the end there. We always.
I think we're gonna prioritize, like, I think we're gonna give, you know, small SU awards to a lot of people, but then we're gonna prioritize, like, right now, our impact project. So I can say like, oh, here's. So you have one of those, like. Something I can like write up and show people. Like, look, okay. Next time. I didn't even understand.
So you're talking about you're trying to make the record a little faster. Have you taken a look at how take on this? You have taken on why then maybe these days you get something to do that. Okay.
So actually, let's say for introduction, you should make if you want to transport it out applications.
So my question
Single step.
See that actually we are seeing
I know, so what I meant is, we have a response that we want to change. Because
Next one, somebody else is big. It's not very direct.
They have all this, or if we get all these stage mode or something.
I'm going to put so what they call it four destinations. So I don't basically and then follow some if they can do it here as well. Just came in me.
Yeah. Well, I'm sure it's fast. So what do you know? So it's really like 6
That's what I even so I actually have written out all this.
Yeah, I don't think so.
That's right.
Why is the reverse of that? Yeah, it's basically. You write the PDF forward, right? Like this, you put the PDF, it was the fact that.
Yeah, I don't think I've ever actually seen like that.
So that's why I thought it was for even some people in the voice, it was for actually different members. Just seeing it all done like every talking about that.
It's actually usually better to go.
So that's one of the things that I used to do. But maybe it might not happen.
Yeah, no.
And if I have time. What, why is the
Not this week right now.
I don't know. I still don't have.
Hey, Georgios. We haven't met in person.
So yes, good to see you.
Good to see you.
How are you?
Doing well. Looking forward to call.
So
Yeah, first year you like everything. There's also like you get the basic of school. The suite, not just the taking costs of where everything's in.
yeah. But yeah, things are tight this year, so.
Spring semester. Maybe it's not the.
I'll figure it out.
Maybe all the motivations.
That's gonna happen.
You know,
There's a big meeting for that.
Yeah.
Whenever Alex gets here. Yeah, that's gonna be.
okay, are you going to Pittsburgh for the?
Yeah.
Yeah, if that's.
I might ask
It's
you
not
if you
much.
take a small package you're available.
So the. They post charges.
Oh, yeah.
16.
Sorry.
Okay, let's get started. George is a new pretty new assistant professor here. This is your second year, right?
Second semester.
Second semester? I thought this was year 2 for you already. No?
In January.
Oh, wow. Okay, starting. Okay, so second semester. So works in computer vision. Generative models. So we're we're really excited to have him here and, I don't know what perceiving humans in 4D means, but I'm sure you'll tell us about it.
Yeah, I will do that. Thank you so much for the introduction, Adam. Thank you everyone for coming. Yeah, so actually, I will talk about what this means, what the 4D means, what the perceiving means. Humans you probably understand. Yeah, my work is in computer vision, and I work a lot with the data from humans. It's I think it's the majority of our visual experiences are focusing on this data. So I think it makes a lot of sense to focus on this problem. Just to give some of the motivation for me at least is that see. Yeah, so from the moment we are born and we open our eyes, we're actually looking at the humans around us. First, it's our parents and siblings, then our friends, teachers, colleagues, and partners. So growing up, we learn how to interact with other people in the world around us by looking at the people that are close to us. And so growing up, we learn from humans, we help them, and they help us, and we can work together. So my argument is that if we want to build intelligent systems that will have similar capabilities, they will be able to learn from humans, help them and support them, or even collaborate with them. We need to endow these intelligent agents with the ability to perceive and understand humans from visual observations. And current intelligent agents can actually see humans. They have the cameras that can actually get these visual observations, but perceiving and understanding what humans are doing is very, very different. And the main problem here, fundamental limitation here, is the disparity between between the visual observations and the true state of the world. So I'll give an unconstrained video here, or a video where people can move in an unconstrained way. You see them going in and out of a frame. If I stop to a particular frame of this video, this effectively is a 2D observation of the world. Meanwhile, the true state of the world here is 3D. So you see how people have 3D bodies and they are in different locations in the 3D space. You see how they can occlude each other. And this extends similarly to video. In that case, the observation is 3D. So you have this spatiotemporal volume of pixels, x, y, t, whereas the true state of the world is 4D. So you see how people have 3D bodies and they can move over time, they can change locations, and they can also change the pose of their body. So these are quintessential examples of inverse problems where we have a set of observations and we want to infer the causal factors that produce these observations. And inverse problems are ubiquitous in computer vision. Actually, this is the goal of 3D computer vision as a whole, as a field. And we do have very mature methods when it comes to static scenes. So in the computer vision area, we have developed methods like structural motion and SLAM that can work on these static scenes. If you are familiar with these NERF approaches, this is what they are doing. They are taking many pictures of static scene, and they are able to generate novel views of the objects in the environment. And these results look really impressive, but if you have seen a lot of those, one observation is that there is never or almost never humans or people in these scenes. Or when they are completely static. So what happened to collect the data for this scene is that people played the mannequin challenge. They stopped doing or moving for a while, and someone took pictures around them for a few minutes. And that works for this setting, but this is not how we are acting in the world. Humans are not really static in the world. Humans are lively, humans are dynamic, humans can move and explore the world. And we want to be able to capture that in 4D. We want to be able to capture the motion of humans from video observation without putting any constraint when it comes to how that video was captured. So for that, my research has leveraged different tools than structural motion and SLAM. So we are actually taking inspiration from graphics, and we use these parametric models of the human body. And we form a tight collaboration with recent advances in deep learning and 2D recognition. And instead of using these models to detect 2D patterns on images, we are actually able to lift the content of an image to 3D and the content of a video to 4D. So this is what I will present you today, like my recent work in this space. So I will give you two different versions of these problems. One is recovering the articulated pose of a person from a single image, getting a 3D pose from just a single image. The second version will be in recovering the full motion of all the people in a scene from a video. So recovering this 4D reconstruction that is coherent and consistent when you see this in the output. All right, so and toward the end, I will also discuss some of the limitations of these methods and recent work that we are doing to push forward in this space. So yeah, as I mentioned, one of the key components for this this type of research is these parametric models of the human body. And one of the most popular and well-adopted models is the simplex model that my collaborators and I introduced a few years ago. So here we start for this large collection of 3D scans, and we learn a low-dimensional representation of the human body. So we have a very small number of parameters. We might go down to 185 number of parameters only. Yet with these parameters, we are able to represent almost any body type and any pose that humans are making in the real world. Now, to give you a little bit more information about what happens behind the hood for this type of parametric models, we start with a skeletal rig and a template mesh, and simple or simplex give us these parameters that allow us to deform and create different poses for this mesh. So, and the very nice thing is that these parameters are also well disentangled. So we have different parameters that control the body shape of the person, and these effectively can change how tall, short, or thin a person is. We have separate parameters that control the body shape of the person. These are the 3D rotation, or the 3D rotations of the joint angles of the person and of the body joints. And depending on the granularity of the model, we could also have separate parameters for the hands as well, for the hand pose. And these are again the 3D rotations for the hand joints here. So this model is amazing. Trust me, I'm using it like for most of my research. But one thing I want to make clear is that this model only describes the forward procedure. So you have a set of model parameters. These model parameters can give you a 3D shape of a person. And then with a rendering pipeline, you can actually render this 3D shape to an image and get these 2D visuals that we see here. In computer vision, we are often interested we're interested in the inverse problem. So the input is actually an image of a person, and we want to recover the 3D reconstruction of this person from that image, or we want equivalently to recover the model parameters that would correspond to this particular person that we see in the image. And the output of this goal is to effectively get this 3D reconstruction that you see here. The nice thing of having a parametric model is that you get a complete reconstruction. So even for parts of the body that are not visible directly in the image, like the back of the person here, you can still get a plausible interpretation of what's the actual reconstruction. And over the years, we have developed methods that are focusing on this problem of lifting people to 3D from a single image. And these methods are quite robust. You can apply them on different poses, like people of different poses in different environments. We're able to reconstruct the hands and get the facial expressions of the people, and even go as far as reconstruct every person in a single image and place them coherently in the 3D space. And our vision, our goal is really to develop these methods that will be applicable to any setting, like really in the wild, so that you can take an image, take a video, and just apply these methods directly, and hopefully get a correct 3D reconstruction of the people there, which is still very challenging. And for some of these more extreme or unusual motions, our methods are failing spectacularly. So you see here that for the most challenging part of the motion, the reconstruction doesn't really make sense. And this is not just a specific example. This happens quite often. For some unusual viewpoints, our methods are failing, our state-of-the-art methods are failing spectacularly. Or they used to fail because we think that we had what we think to be an important breakthrough here that would allow us to go from the previous state-of-the-art that you see on the left to the reconstruction that you see on the right. So these are frame-by-frame reconstruction. There is no temporal smoothness here, and from every frame you can get this reconstruction of the person doing the high jump, and you can also get like a very plausible interpretation of this motion as well. So how we achieve that? This is part of our recent work that we presented in ICV last year. It's called Humans in 4D, or also called it 4D Humans. And I will describe what we did for this work, and I will also try to give some context of how we get there, or how our approach developed over time for the last few years. So for this, in this problem of lifting humans to 3D, or honestly lifting any object to 3D from a single image, this is very challenging. Just some general problems that you have to deal with is that you have the monocular ambiguity. There are many plausible 3D interpretations of the same 2D image. You don't have images with, or don't have a lot of images with accurate 3D ground truth, so you can get this detailed mess only if you actually capture the people in a laboratory environment, so you don't have the data to train networks in a fully supervised manner. And also, it's not something that humans can annotate, like you cannot ask people to annotate metric 3D information from images alone. So we had these bottlenecks. This is quite general in this type of single image to 3D problems. The way that we were addressing this issue, or the first paradigm that we developed to address these issues, was by first building this bottleneck of first detecting 2D key points on the person, and those are just pixel locations, the 2D pose of the person. And this is a task that neural networks excel at, because humans can actually annotate these pixels on a lot of images. Can train large networks on this task. They are very good. So you do this first step using neural network, and then you want to go from these 2D key points to this 3D model. For this, we develop a model fitting approach. So we have we pose an objective function that has two main terms. The first one is a data term based on joints reprojection. So we want the projection of the 3D joints of the person to align with the corresponding 2D key points on the image. That's the main objective we have. And we also heavily regularize the solution here. So we add a number of priors, handcrafted priors about what we believe to be a valid pose, what we believe to be a valid shape here. And at test time, we minimize this objective using iterative optimization. So you can see on the right what happens during this optimization. We start from the mean pose, and then we gradually update the mesh such that it aligns and explains the image observations. And that's a process at this point is more mature and works pretty well, but it's quite slow because this needs to happen at test time, this iterative optimization. So we have also developed methods that are rely that,
Can I ask you a
yeah,
question?
yeah,
about
of course, of course.
that? Is that not an underspecified problem? Like, aren't there like the second half of it?
Yeah.
Like, there would be multiple shapes and that ought to
yeah.
fit that skeleton, right?
Absolutely, yes, that's a part of the monocular ambiguity problem. So this is one here we're getting one interpretation. This heavy regularization is what helps us to get let's say, one of the most plausible interpretations here. But we are only, at least with this approach, we only get one 3D interpretation. We don't get, you might want to get like maybe probability distribution of plausible poses. Here we only converge to one solution, typically one local minima. It's unlikely you get the
Like
global
of the
minimum.
ones that you could get from that skeleton, presumably there's ones that people would judge to be better or worse, and you're using the priors to guide towards the ones that, or this regularization is like, are you evaluating whether you're getting the one of many that people like, or?
It's not what people like. So here, this is typically evaluated on some data that we have from a lab. So we can put like, we have like 3D ground truth to evaluate the accuracy of this optimization. So this is evaluated with golden standard, not just what people prefer, but golden standard 3D ground truth from mock-up systems. These priors, and then, how you weight these different terms, what type of priors you use, play a big role here.
So it's underspecified from the skeleton, but you do have a ground truth label that you use to regularize.
When it comes to evaluation,
I see.
not regularization at test time, we don't have anything. When it comes to evaluation, this is done properly with accurate 3D ground truth to get the full picture. Yeah.
Thanks.
Can you use a nerve?
So this is a mesh-based model. On top of that, you can build an avatar. Like I will show some examples later, but this is just the mesh surface of the person.
I wanted to go from the 2D image to 3D image. I could use a nerve.
If you have only one 2D image, it's just too underspecified. I mean, nerves work with a lot of views. So that's the result I saw in the beginning. If you have a lot of views, you can actually do it. If you have only a single image, you do need heavy priors that some nerve methods have incorporated. Here it comes a little bit more naturally.
But in a video, I have more.
But it's also dynamic, so that makes things even also complicated. So that's why I said I saw this mannequin challenge example in the.
Okay, so it's not known. So it's not known how to do it with a nerve. Wow.
In most cases, even nerve approaches start with this because they are proven to work quite well. You have an initial estimate of the rough pose, and then if you want, you can actually start optimizing or updating it to fit also the image pixel observations. So I was saying that these model fitting approaches tend to be quite slow at test time. So we have also developed approaches that are based on deep networks that can deep network will directly take an image of a person and regress in one shot the parameters of this parametric model and give us a 3D reconstruction. What we observed while developing these methods is that an obvious comment here is that as I said, we don't have 3D ground truth to train these networks in a fully supervised way. So for this in the wild images, there is no actual 3D ground truth. What we did was to actually use the model fitting approach as the supervisor for this network. So a iterative optimization model fitting approach takes the initialization that comes from the output of the network, and then we gradually update this pose such that it aligns with the 2D key points on the image. And this final output can be used as pseudo ground truth to train the network in a fully supervised manner. It's not perfect ground truth, but it helps the network converge better because it gives access to some plausible 3D pose parameters. And typically, we use a combination of in the wild data and data from the lab with actual ground truth to train these networks. So
how do you find those 2D points?
Those are, as I said, because those can be annotated by humans on images. the methods we have and the networks we have are quite reliable at detecting them. So these are all typically automatically detected on images, and with good, you can assume we're quite reliable there. All right, so yeah, these are the more recent approaches, the more modern approaches for this task. This is what we followed also in this work that in the latest work that we have in this space. A deep network that can take an image, regress the parameters of the simple model, and then passing this to the simple model will give you this output reconstruction. We did follow this deep network paradigm, but we actually put this on some extent on steroids. So this paper was an exploration of how far we can go by pushing primarily the scale of the model that we use and the scale of the data that we use to train these models. So avoid all the bells and whistles, just try to scale up on these two axes here. And this was, I would credit this phrase to Ray. For me, this was a lesson of how I learned to stop worrying and love big models and big data. This was the exploration that we did here. So the first victim was the model. So instead of the convolutional networks that we used until a few years ago, we substituted this with a large-scale vision transformer, which seems to be scaling much easier for these visual tasks. So we pacify the image, we pass it through the vision transformer. Of course, this is not, I mean, the devil is in the details here. So it's important to do all the steps right. So you cannot just plug in vision transformer. You need to first do first stage of pre-training, where you will train with this MAE or mask autoencoder method, where you drop some of the patches and you give the rest of the patches in the transformer, and you try to reconstruct the full image. This is done on ImageNet. This is an unsupervised form of pre-training. That's the first stage. Then there's another stage where the network is pre-trained specifically on human data, but for the task of 2D pose estimation. This pre-training was also important. So we only estimate 2D key points here. When we have done these two stages, we can actually go into the final architecture, where we have a fully transformer-based design to regress the parameters of the model and get this 3D reconstruction in the output. And just to give a scale of what we used here, this was almost 25, the backbone we used was 25 times larger than the regular Resident 50 that we were using until a while ago. So this was on the model axis. Again, simple design choices, just scaling up.
Is there a DQV you're using? What tokens is the transformer looking at? The output of the transformer?
The patches of the image.
How are they tokenized?
Those are just passed directly, like you just yeah, in the vision transformer. Yeah, you don't need tokenized. Yeah. So this was on the model parameter, on the model axis. Yeah.
I don't understand what's the motivation behind using these deep networks. So, for example, even for the CNN case, you were passing the image to CNN, but you could, in principle, also generate that 3D image using model fitting, right? Like, what's the motivation? The
one motivation is that this is much faster at test time, so it's more practical to actually have like this feed-forward approach compared to the using the iterative optimization. The other approach, again, also from practice, what we observed. The model fitting approach is much more prone to starting in local minima. So it depends much more on the initialization that you might have. Whether that's good or bad, that can actually get you into a bad local minima potentially. The deep network was much more robust, less precise, but more robust in general.
But if you're using those model fitting outputs as the ground truth, isn't that the case that the deep network will also be?
The nice thing is that goes into more detail, a bit more details here. But because this is used in the loop, the model fitting approach is using the initialization from the network. As the network improves, the initialization also becomes better. So the model fitting converges to better fits in the output. So this is kind of a self-improving procedure that over time you get better and better 3D grounders to train the network. So that's kind of a more alive mechanism, whereas that really depends on, it's more depends on the initialization and can be more prone to failures.
Thank
you. All right, so that's about the model axis. On the data, yes, I mean this model, of course, you need to really supply it with large amounts of data really to see the benefit of this deep architecture. We of course use whatever was available before. This was like almost 500,000 of images, most of them indoor with 3D ground truth. We scrape the internet. We use images primarily from Instagram, almost an order of magnitude more images than before. 5 million images. Those are not coming with 3D ground truth, so we use this pseudo ground truth generation procedure where we start from an image, we get an estimate of the pose of the person, and then we try to fit these to the 2D key points such that we get a better 3D ground truth. So all the best practices for this for this task, just to see how far we can go.
And this is the approach that would just takes too long at deployment time. If you could use this, that's the conversation.
That's exactly. So exactly. So that the thing is that this can be plugged in on any network output. It has some extra overhead in the optimization.
But here you're just doing it once in one really big
offline
computational process for all of this 4 million.
Exactly. This is done offline once, and then so that's the more or less best practices in this space. How far we can go? Pretty far, actually. Here we just tried this on large variety of images and video. Primarily, we tried these more extreme motions from rhythmic gymnastics. We tried it on regular gymnastics. We tried it on track and field. All those results are per frame results, so there's no temporal smoothing done here.
Why were there little people sitting on the balance beam bar?
I think there are some in the background. I think these are the judges. We don't really, I mean, this is a model reconstruction, so we don't really account for the occlusion. We don't really account for the occlusion here. These are judges sitting behind, I guess, the bar. So yeah, that's the kind of also gives this a model reconstruction. Yeah.
And how long does it take to generate one of these videos? Like,
that depends more on the GPU, but it can be like even in real time. Like a forward pass can be done in 30 milliseconds, so you can reach 30 FPS. So there are often some pre-processing stages. You might want to crop the image, like to detect the person in the image, crop that, pass it to the network. So the whole processing might be a little bit more expensive in an actual demo. But the forward pass of this network on a reasonably recent GPU is 30 milliseconds only. And yeah, we evaluate this like extensively on the standard data sets on both 3D pose estimation. Here we actually have 3D grounders to evaluate against, and these are previous state-of-the-art methods. Our approach improves over the previous works, so lower is better here. We also tried on in the wild images. So here we only evaluate 2D pose, how well the 3D pose aligns with the 2D key points of the body. Here higher is better. We perform better than the baselines. I mean, this is quite populated area. We didn't just compare with two methods. There's like a whole table with all the methods that we had to compare against, but the evaluation is very thorough, like with the state of the art here. And
did you evaluate like depth? Is it sort of depth aware between two humans and then?
Yeah, that's a very good point. So this is because you still have the scale ambiguity. So we are not really recovering actual metric scale of the human. Our scale is more or less an average scale, an average height of a human, regardless of the input. Or we are not doing a good job at that. You could potentially do it. We don't evaluate that. We use some cues. I will talk about briefly about what cues we use for that, but this is not our biggest strength, I would say. These cues are not, we don't leverage these cues for relative depth between humans.
Have you ever considered to use a function, 3D function model like Duster to reformulate it to predict the human parameters? And since it takes more than one images, and you can reformulate the video at the incremental reconstruction.
That would be a good idea. I think that Duster still needs like a static scene, so it's like if it's dynamic, they don't need to be adapted.
But we can have different head to predict the human parameters.
Right. I see what you mean. Yes. No, I think that's possible. Or there are different ways to deal with the temporal problem. This is like the most kind of the bare bones, like single frame problem. I think that Duster would probably not be help there.
In principle, Duster can it is pre-trained with the kind of video 3D data, and it should be predict the consistent video frame. Not video frame, but let's say if you process frame by frame as stereo input, so probably in principle it should be better than
I'm only concerned for like this extra step of also handling the dynamic humans. That would need some extra step. Like it's not just static scene as Duster has seen before. So I'm curious to see how this would be handled there.
But as long as we have the video data and the poses, we should able to have this foundation model for the human pose estimation.
No, I do consider that like a form of foundation model also.
I also here. So let's say we have a lot of octave flow network, and we also have the Duster.
Right. No, I think that's definitely interesting to try, like to see what you can get out of this. I haven't seen people merging the two at least in the human space. I think that's worth exploring.
I'm trying, but it seems the network is very hard to converge.
The Duster network.
Duster and octave flow network.
I see.
Combining together.
I see. Yeah. Now these methods have been developed to be quite robust at this point. Like all the recipes and the secrets are there, so we're in a better state. I was going to actually show some qualitative results also of how this compare with different approaches. So on the bottom you have the previous state of the art. On the top right we have our approach. But I was going to say also, I think that's a good point. Like we did try to, or in the process of developing this approach and looking at what matters for this problem, we also started to rethink that our approach here, instead of this is a model that does only this single frame reconstruction, to this is a quite powerful model that is very robust in most cases. This could be considered as could be thought of as a foundation model for 3D humans in general. So the output could be relevant also for other types of tasks. And one of these tasks that we showed the benefit of our approach was the tracking task. So here you have a video and you want to first associate the people in the different bounding boxes. So this person with the red set with that person, and the person running with the person running in the second frame. This is typically done in the 2D images. What we propose is to actually use our 3D reconstructions to solve the association here, to match the people in the two different frames, or for the duration of the video. And this uses the cues that we have from our reconstruction. So this uses the 3D pose. This uses the 3D location, what you asked later. So the 3D location is not super accurate, but it's often a good cue to, if people are of approximately the same height, we can place them reasonably one with respect to another. It's harder when you have like kids, when you have like people of different height there. So yeah, this is, here we deal with this tracking problem. And that's why you see also the color of its tracklet being consistent over the duration of the video, because we are able to redetect and track the people using our 3D reconstruction, even during occlusions, which are often problematic for many 2D tracking approaches, even for very challenging occlusions where you see very, very small part of the people. Sometimes you can still retain the tracking properties here. And we try this also on some team sports as well. And yeah, we evaluated also with previous approaches, and our tracking, our 3D informed tracking was outperforming previous state of the art that was often built specifically for humans, specifically for tracking on 2D images. We could still get better performance by this more rich information that we capture in our tracking. So you don't have just like a soup of pixels, you have the actual 3D pose of its person. So this is one task that we try to demonstrate the benefit of our better of this improved model. The second task was related to action recognition. So we demonstrate how using this information from the reconstructions, the 3D pose of the people, the tracklets over time, this is orthogonal to what the current systems for action recognition are using. So if you combine these 3D features with the existing 2D features of previous approaches, you can get a healthy delta compared to the state of the art. So this is just more evidence that the model is quite strong and can be used also for other downstream tasks, and can be potentially thought as a foundation model for 3D human tasks here. So,
George,
yeah.
question. Is this reasoning in 4D or just per frame?
This is I think there is some tracking. So you do the input is a particular the prompt is, let's say, a frame and the bounding box on a specific frame. We take the tracklet, the history of the tracklet before and after to have like a more extended temporal window there. So it's actually 4D. Yeah.
So this produced by feed-forward model or perceptual optimized model?
Oh, this is feed-forward. Feed-forward model. Yeah. Yeah. So the code is available. Like, we are big supporters of open source, like code models, data, whatever we have used. Like, just you're welcome to, and you are encouraged to try it if it's relevant for your problem. Yeah.
Do you think like adding explicit depth information, like molecular to depth models?
Yeah. I think that when it comes to the local pose, like, disambiguating which body parts are closer to the camera versus which ones are further away, these depth estimators are not doing a good job, particularly because you have like this thin structure. So I wouldn't trust it so much for improving the local pose. I would trust it to maybe give us a better estimate of the location of the person, the depth of the person in the space. So location, yes, I think this could have like orthogonal information. For pose, I believe that this is better optimized for this particular articulation estimation of the person. Yeah, and just to show that this was not an one-off, and that this kind of approach applies to different settings as well. We also had a follow-up work that we did the same for hand pose estimation. The recipe is the same. We take this large model that we train with a large amount of data. This is like 4 times more data than what previous approaches were using. Again, train all the best practices that we learned before, and this leads to this very compelling model with very compelling results. We tried it on a variety of settings with this is contact juggling. We tried it on cases where you don't have any context about the rest of the body. This is like the hand from the Addams Family. In cases where you have like playing instruments, kind of out of distribution data, like animated films, for cases with people performing sign language or performing specific gestures here, or even egocentric data, which are very popular recently. And the interesting thing is that our model has never seen has never been trained on an egocentric data set, yet it performs gets quite compelling results here as well. Yeah.
So question, so you have separate models for the hands and the body and everything. So when you showed the people doing the backflips and stuff like that. You were there's their hair also that's getting flopped all around.
Oh.
Like, if you wanted to add like another tracking thing, like either hair or like clothing or like something like that, how much effort would it be to add another component to the tracking?
So I believe, I'll be honest here, that the current models are reaching their limitations when it comes to modeling with the same kind of paradigm. So these are kind of mesh-based models. So you model the deformation with meshes. You can capture hand pose, you can capture facial expressions, you can capture some deformations for the feet with specific parameters. I don't think that these mesh-based approaches are the better fit for modeling clothing, modeling hair. That would probably need more nerve-based representation. They are on top of the this parametric on top of this surface that we already have. That's how I envision this would happen. We don't have something that is diverse enough, I would say, or like something that would capture the whole diversity of clothing in particular. For hair, I think the attempts are better, like people from graphics have done good job already to model, even with parametric models, the hair of people. For clothing, I don't think it's there, at least to capture this wide variety of clothes that we have in images.
I mean, it's one thing for hairstyle, like that's static. It's another if the hair is going to be flopping.
Oh, I see. Yeah. No, I mean what I have seen is like modeling this. Okay, here is like hairstyle. Can you actually reconstruct it? Modeling the whole dynamics. Yeah, that's even further away. It goes a little bit more from kind of my motivation that, like, it's, yeah, I'm interested in 3D, but I'm interested like in 3D to the extent that, how we can perceive the humans, and some of the clothing or the other features of the appearance are not the primary target, or like they don't carry most information there. Yeah, that's I think that's an active area of research here. Yeah.
What are the big differences between like modeling pose and hands versus facial expressions?
It's handled slightly differently. So the facial expressions are the people learn this like a PCA space of the on the vertices of the face, whereas for hands there is actually articulation modeling. So there is a 3D rotation that deforms with linear plane skinning, with symmetric from graphics, deforms the joints, deforms the mesh, and kind of poses the different joints. Whereas for face is fully data driven. It's based on PCA. It has captured many people in different expressions. They try to learn a PCA space of the different expressions that people are making. So this can fall under the same framework because everything is mesh based. But yeah, the representation or how it's handled is slightly different here. And yeah, at least one of the what makes us happy for this work is that people are really adopting this and they are using it for their problems. So this has directly been used for works on hand-object interaction. So people are using it to model interactions of hands with objects. People are using it for imitation in robotics. On the left, I have work like from Yukas and Peter's lab that they used this hammer model that we have for hand pose estimation. And we have also been using this for building avatars. This is building photorealistic avatars of people or of hands. Specifically, this is work that on the left, you see work that was led by Hezen, that was a collaboration with Atlas here. But yeah, this was one of the successes for us. People are actually using this for their tasks. And of course, again, code models, everything is available, and you are encouraged to use it as well. Am I reaching close to time, or we're finishing at 1? Or?
I mean, yeah, we usually stop at 1, at like a little around 1, but if you want to take 5 more minutes, up to you.
Okay. I will just I won't. I don't think I have time for the temporal reconstruction that I had planned for. I will just go closer to the to some of the results. What I wanted to say is that with this approach, we are able to, with the approach I will show you, we are able to position the people. We are able to position the people in the image. They look pretty good. Sometimes it's more jittery with these kind of results that I showed already. But as a word of advice if someone is working in 3D computer vision, they are showing you some of the results, you should always ask them to show you the results from a different viewpoint. And this is where you can see some of the limitations that we have here. So you expect that all the people will live in the same row here, but you see how much more jittery it's in this along this dimension. So the reconstructions that we get from these feed-forward models are not completely reliable here. And this is an example with static camera. The results become even worse if the camera is moving. So you see here how people are almost flying in the space in the more challenging scenario. So what we have proposed to handle this 4D reconstruction is an approach that is jointly consider the human motion and the camera motion as well. I just want to give you just a few snippets of this of what happens here. This goes back to this model fitting optimization. I think that for these temporal problems, it's harder to actually have the full fit to have just a single feed-forward network to model everything. So for this approach, we take a video as input, we apply our method on each frame separately, and we track the people. The extra key thing is that we also track the camera motion, and this we can get this from a SLAM or an SFM method, and we combine everything together with a global optimization that gives us this consistent 4D reconstruction in the output. And this, again, because I think this is where the limits of model fitting versus regression approaches lie. For these temporal problems, I think regression approaches are still struggling behind. The model fitting approach is the more appropriate here. So we have the objectives that I described earlier based on joint projection and the set of priors. We want to have like a valid body pose for each person and body shape. We add the extra thing that we can add here is some smoothness term to make sure that the reconstruction, the world frame is actually consistent over time. And because we also recovered the floor, I'm not sure if it's visible here, we also have some environmental constraints to avoid the sliding and interpenetration with the floor. So that's kind of how we are currently dealing with this temporal reconstruction. And just coming closer to the end, yeah, we'll show you some results of this. Again, this seems to be quite robust here. It's jointly models, as you can see, how the camera is moving and how the people are moving in the space. So it's the best system that we currently have for this. And if you combine it with best tools for the reconstruction, you can see you can get both the pose of the people and their displacement over time, the actual location in the field, and hopefully also the height. I haven't tested that for accuracy, but you can see how the person is actually jumping high above the ground here. So these are currently how we are dealing with this 4D reconstruction. This is it is still, I think, more of an open problem, like this single frame reconstruction, but we are getting there, hopefully. And just to show you some of the limitations, hopefully to point where the future work is going, all of this is really not considering any of the laws of physics. So it's like you can't have these interpretations, you can't have like unusual forces here. We have work that is trying to put these results into a simulation environment so that we at least have some physically consistent reconstruction as well. This is also more of an open direction that we're looking at. We are having more challenges when people are close to one another or they are in contact. And this is kind of different thread that we're trying to follow. It's even harder because sometimes the actual height of the height of the people varies a lot, and that's something that it's hard for us to capture from a monocular image. Here we have a child that is not easily, you cannot just reconstruct with the methods that we had out of the box. And then even looking more further into the future, we want to also integrate this with the scene, reconstruction of the scene, of the environment of the people that are moving. with the objects that the people are interacting. So we have this kind of joint hand and object reconstruction. And I think that this is where the problems become really harder. And this really needs this object based reconstruction really needs different tools. We have ongoing work that I'm very happy that this is like this actually comes from UT, like from my lab here, and trying to reconstruct any type of object from single images. This is work led by Hanwen together with Tsing. So these are just like give you some idea of things that are open, things that are still very challenging in this space. And yeah, I think I can conclude here, and I would be happy to answer any questions. Thank you.
For the last work you presented, you showed a lot of objective terms.
Yeah,
yeah. How extensive was your hyperparameter tuning? Like, was it very hard to adjust?
These are typically very hard. The good thing, at least, because these are you can think of these as systems that we have built over time. So some of these works go back to 2019. We do have the experience to know what works well for a single image, and then every time we add an extra term. So it's a more constrained parameter search. We don't search all the parameters for all the objectives. We know that this works for a single image. Okay, we have one more temporal term. How to balance this with the others? Some hyperparameter search. Oh, we want to add another term that is based on the environment. Search that separately. A global search of all the possible hyperparameters, that would be too hard, particularly over video. These methods are also quite slow. So yeah, that's a good question. We have developed the good practices, I would say, and the background to do that more efficiently.
How does that compare to the regression models? Do you have to do as much hyperparameter tuning?
It's for regression models, it's often it's often easier. With that being said, they are often on a single frame. Again, as I mentioned, the temporal reconstructions are still getting a 4D reconstruction with a feed-forward model is not quite reliable. So these things are not really working so well anyway. But for single images, yeah, the feed-forward models are quite easier to tune. One reason is that you have, I think of these regression models as one model that can handle any image or any input that you give it. These optimization approaches, sometimes you might see very different results depending on what tuning parameters you have on the different examples. So you really need to search a large number of examples to tune your hyperparameters on many examples. This is very costly. Whereas for the feed-forward network, you train it once, you try it on dataset, looks good, no, continue with a new hyperparameter. That's typically the cycles there are faster.
So you do this at the frame level, right?
For the temporal reconstruction or for
the model fitting?
Some of these results are 4D, so they're over time also.
Over time.
Yeah.
Okay,
so there is a smoothness term, there's a motion prior also for this last work to account for what is a valid motion of humans in the space.
Are there any constraints regarding the resolution and the frame rate of what you can input into this program?
Yeah, so the resolution, we are getting better at that. A few years ago, it was harder to go below 50 pixels. I think that some other methods work well with lower resolutions than what these parametric methods are doing. For us, if you go below, I would say 30 pixels, it's there's very little information there to go for. At least for humans. For hands, it might be a little better because our hands often are very, very small anyway, so they work reasonably also in lower resolutions. For people, you want them to be above 40 pixels or 30 pixels to work reasonably.
Well, I just got one question for the humans in 4D. Does it influence has the difference of the motion speed? Will it impact on the final inference result?
Say it again. If the motion
if the motion speed varies.
Yeah.
where is
I mean, if the motion for the humans in 4D, because it's run on every frame separately, if there is like high motion blur from fast motion, that could be a problem. But in general, it's not a big issue. Like I think that it's mostly that if you see the errors that you see in the results are mostly motion blur. Like Simon Biles rotate so quickly that 30 FPS you cannot. In one frame the fit is here, in the second frame you interpolate and it becomes here. So you see